So for this lesson, we're going to take what we learned in 4.2 and we're going to apply it using what's called the first derivative test. So this is what we know so far. We can find critical numbers. We can find intervals of increase and decrease based on when the derivative is positive or negative. And we can find the absolute maximum or minimum of a function defined on a given interval, a closed interval. This is what we don't know how to do yet. Given the critical numbers, whether those numbers represent a maximum, a minimum, or neither, and how to determine local maxima or minima of a continuous function for an open interval. Finding the critical numbers and knowing what is happening at those critical numbers are two different things. We can analyze the sign of the derivative, the slope, using intervals to determine where the derivative is positive, where it's negative, and where its sign changes. This information will tell us what is happening at each critical point, and this procedure is called the first derivatives test. So, if I use a critical number like c, if my f prime of x changes from a positive to a negative at that point, then that is going to be a local maximum. If it changes from negative to positive at this point, it's going to be a minimum. If it goes from positive to positive or negative to negative, it is neither a maximum or a minimum. Remembering that for all of these, f prime at c is equal to 0. So for all of these examples, they would still look like critical numbers. It is important to know the domain over which a function is defined. So for each question, we're going to start by stating the domain. So for our first example, what are the local maximum and minimum values of f of x is equal to 1 minus x over x squared plus 3? Well, to start with, we're going to do the domain. And for the domain, we're looking at that denominator, which could cause restrictions, and we're going to say x squared plus 3 cannot equal 0, which means that x squared cannot equal negative 3. And when I try and square both sides, there is no solution for that denominator, which means that the domain in this case is going to be XER. No restrictions on that domain. The second thing we're going to do is we're going to derive. And we're going to say f prime of x is equal to, well, we need to use a quotient rule in this case. So we're going to take the low times the derivative of the high minus the high times the derivative of the low, all divided by the low squared. This is going to give me negative x squared minus 3 minus 2x plus 2x squared, all divided by x squared plus 3 squared. I'm going to keep simplifying, and I'm going to get x squared minus 2x minus 3 divided by x squared plus 3 squared, or when I factor it, x minus 3, x plus 1 over x squared plus 3 squared. The next thing I'm going to do is I'm going to get those critical numbers. Well, I'm going to take the f prime of x is equal to 0, or do the numerator is equal to 0. And I'm going to do the f prime of x does not exist, or the denominator is equal to 0. In this case, I'm going to say that if x minus 3 times x plus 1 is equal to 0, then x is equal to 3 or negative 1. In this case, if x squared plus 3 squared is equal to 0, then x squared plus 3 is equal to 0, x squared is equal to negative 3, and there is no solution in this region. Then I'm going to do my first derivative test. And what I'm going to do for my first derivative test is I'm going to create a number line. I'm going to split it up based on those critical and significant numbers, so negative 1 and 3. And then I need to pick a number that fits into each of these regions. So let's say that I'm picking something along the lines of negative 2, 0, and 5. Now, when I sub those back into my derivative, what am I going to find? Well, when I put it into my derivative for negative 2, f prime of x is going to wind up being positive, and then negative, and then positive. What does that mean for my f of x? It means that it's increasing, then it's decreasing, then it's increasing. And as we already know, when it changes from increasing to decreasing, that is a local maximum. When it changes from decreasing to increasing, that is a local minimum. And then I'm going to use that for part 5 to solve my y values. So I'm going to take f of negative 1 is equal to, using my original function, 1 minus negative 1 over negative 1 squared plus 3, and that's going to give me 2 over 4, or 1/2. Now, because this existed at point of 1, that is my local max. If I use the second possibility, f of 3 is equal to 1 minus 3 over 3 squared plus 3, and that's going to give me negative 2 over 12, or negative 1 over 6. And lo and behold, I get my local min. And then I can state, therefore, I have a local maximum value of 1/2 and a local minimum value of negative 1 over 6. When it is approaching the point of -1 from the left, it is greater than 0. When it is approaching -1 from the right, it is less than 0. So because I went from a positive to a negative, or greater than 0 to less than 0, then that is going to be a local maximum, where x is equal to -1.